Hello, I'm gonna start the record of this progress video. The first paper I'm gonna introduce is Entropic Causal Inference, Identifiability and Finite Sample Results. This paper deals with a structural causal model for two variables, and the assumption is as follows: for given two variables x and y, the one of this causes the other. In the case of x causes y, the corresponding structural causal model can be represented as y equals f of x and e, where x is an exogenous variable representing additional randomness independent from x. So the framework of entropic causal inference can be introduced as follows. First, consider the deterministic systems. For the deterministic systems, we have no randomness for the exogenous variable, so the entropy of the exogenous variable is 0. In this case, since the system is deterministic, with high fraction, the model can be identified because most of the functions from the set of n elements to itself is non-injective. Then, how loose can be relaxed the entropy condition to guarantee the identifiability. So the pre-work of this paper conjectures them. So the conjecture is as follows: for some uniform sampling condition assumption, the entropy of exogenous variable can be relaxed to the log of n plus for some constant. And this paper tries to solve this conjecture partially. So for under some uniformly sampling assumption, at least the constant entropy exogenous variable is permitted. So to see the proof of this, first we're going to consider the minimum entropy couplings. The minimum entropy coupling of t variables, u sub 1 to u sub t, is the joint probability distribution P with minimum joint entropy. And why is this important? Is because in the paper of Kokaglu, they proved that the entropy of minimum entropy coupling of the distributions, the conditional distributions of y given x, is equal to the entropy of the minimum entropy exogenous variable. So one can convert the problem of the minimum entropy exogenous variable into the entropy of minimum entropy coupling of conditional distributions. And also, one needs to deal with the finite sampling, the finiteness of the sample. So the natural way of to deal with the finite samples is using empirical estimators or so-called plug-in estimators. So a natural way to approximate the given distribution is using this like empirical distribution, which is simply the sum of indicator variables over n. And also the conditional distributions like this can be defined in an estimated manner. So we want to approximate the conditional distribution P of y given x by P hat of y given x. To do this, the paper proved a lemma and a theorem. For the lemma, this lemma states that the plugin estimators approximate the given distribution well. So when the number of samples n is large enough to the is like n to the 4 times log of some power of log, then the conditional distribution and its estimator has their difference is bounded by 1/n squared times log of n, and vice versa. Given this 1/n squared log of n difference, one can know that the entropy of P and Q are not that different. Their difference is at most 3. So we converted the entropy problem into one of the minimum entropy couplings of conditional distributions, and the following 2 theorems in the lemma show that we can approximate the conditional distribution with its plugin estimators, corresponding plugin estimators, and they work well. So by combining all, we can prove the desired theorem. So as a plan from now on, I'll do the experiments in the paper, and I'm gonna reproduce the experiments with using synthetic data sets. If the time permits, so there are 6 or 7 experiments, and except for the last one, they use synthetic data sets. So I'll reproduce all of them, maybe. And if the time permits, I'll do the last one as well, using the Tübingen cause and effect pairs data set. And for the second topic, the professor recommends 2 papers: the men also like shopping and directional bias amplification. And the directional bias amplification extended the work of the Zhao men also like shopping. So these 2 papers deals with the bias amplification problem. The problem states that the trained algorithms amplify the bias existing in the dataset. So for example, let's say there are data sets which have more examples which relates women with cooking than the men with cooking. Then the algorithms trained using this data set is biased towards the cooking woman than the cooking man, so that it can misclassify the some cooking man as a cooking woman. So as a problem setting, there are 2 categories. So the demographic groups, and the same one for the tasks or targets. So let's say there are a set of protected demographic groups, and the binary random variables of each is the corresponding binary random variables can be defined, and the same work can be done for the targets. The Zhao's work in the men also like shopping is as follows. So they introduced a metric called RBA, and it is defined like this. It is defined as 1/t, the 1/the number of tasks, and the summand is the difference of this conditional probabilities, given that some kind of positive correlation exists. So this y sub at means that the condition, some positive correlation between a and t exists in this direction. And there are some problems as stated in the directional bias amplification paper. The metric focuses on positive correlations because there are no negative y term. There are only a positive y term. And the chosen protected group may be incorrect due to imbalance between groups. And the errors from demographic groups and the errors from targets are indistinguishable. So they proposed these more refined version of the Gauss metric. They defined like this. And to the first glance, we can see that there are 1 minus y term here, which is entangled with negative delta term. So this summand, the authors considered the direction of each bias to the summand. So for the positive correlation part, the similar delta is used, and the negative part, they switch it a and t. And as a plan from now on, also the experiments will be reproduced as the source codes are available for both papers online on the GitHub.